I mentioned Tears of Joy in any of the orientation videos, but I did have a student cry from Tears of Joy. 152 student. She struggled and struggled and struggled and finally she had the highest grade on the test. That put her in tears. And my eyes welled up once for Tears of Joy from grading an assignment. So, not streaming down my face, still the hope. This class is going to do it for me. The six who dare. Okay. Any questions? Okay. Doris, do you have any questions? Okay. All right, so let's sort of start. This is the first bit for the stuff that is beyond the next test. So we start out with a scenario. I have an object A that is heading to the right. I have an object B that is heading to the left. They will collide into each other at, we'll just say at this point right here, that they will hit. They will move a little bit as they are both sort of turning around, and they will bounce off of each other. So let's say this is the point in which so this is when they first make contact, this is when they last make contact, and that marker is sag, and then they will bounce apart. So, while they are in contact with each other, there are three quantities that are the same for both objects. What are the three quantities? And just add a little bit of excitement. Okay. Do you want to narrow that down some?
Between two objects.
How do we know that the normal force cannot be the same between both objects?
Because in the third image, A has pushed past where it meets B, it's
That's not the reason.
Because they're not.
Say it again?
Because they're not pushing, deforming their shape, I guess.
Nope, that's not the reason. What do you know about forces?
In equal pairs.
Okay, and? What do you know about the forces in a pair?
Equal but opposite.
If all you say is the normal forces are the same, they cannot be because their directions would be opposite each other. So, what is the same?
That there is normal force. Present.
We can do better than that. You practically said it a moment ago. And Ethan hit upon a key word just before you said it. Together they have the answer.
The force of the normal force but in opposite directions.
Magnitude of the normal force. Yeah, Ethan said magnitude, you said equal. The magnitudes are equal. So that is one of the quantities that is the same. I'm going to do a shorthand notation here that the force on A from B, I guess the magnitude, is equal to the force on B from A. So the magnitudes are the same. I can write this slightly differently without the absolute value marks. The force on A from B is equal to the negative of the force on B from A. This is Newton's third law in shorthand notation. The magnitudes will be the same, the directions will be opposite. All right, so we've got one thing down, we've got two more quantities. And I will say, one of the quantities is so incredibly obvious, it's usually one of the last ones mentioned. Occasionally somebody gets it early, but one of them is just incredibly obvious. We have a limited number of quantities. Oh, by the way, forces, done. Do not mention forces again, otherwise you'll start getting body parts.
Does weight fall under forces?
Yes, it does.
Okay, that's
I would assume you did not say weight, and just asked a question about it. And the weights aren't necessarily the same, anyway.
Is it the material that's sliding
They're not necessarily sliding on any material, it's just, in this universe, I just have these two objects running into each other, there's no other object involved.
Their momentum.
Their momentum is not the same. The remaining quantities are quantities we haven't talked about.
on? Direction?
Direction's definitely not the same. And when I say quantities, quantity is something that can be measured.
Does that have to do anything with Newton's, or is that the person?
That Newton's deals with force, that's already been taken care of.
Their speeds?
Speeds are not the same, because I don't know how fast they're going before the collision and when they hit. I mean, there is some play there where they have to turn around. But speed is not the same.
Distance one,
What do you mean?
like, from, like, where they, like, the dotted line from, like, where they set, right?
We can be more specific.
It's not distance.
Yes, it is.
It is. Oh.
A, if we think about the center of mass of A is gonna go from, basically, that is gonna be the displacement of A while they're collided, and B is gonna be doing that. They will displace the same. So the displacement of A is equal to the displacement of B, and my nice little ideal scenario here. And the last one, the one that is so incredibly obvious that Luis is going to tell us without even knowing what the question is. And the answer is
Your mom.
my mom. Did you mean your mama?
Your mom. I'll,
Yeah, what are you gonna say about it?
7?
No. Okay, I was wrong about his just saying it without knowing what the question is. It is neither my mom nor 7.
What's the question?
You just wanna know everything.
Yeah.
The question is, while these two objects are colliding with each other, there are 3 quantities that are the same. We've established that they will exert same magnitude of force on each other, but opposite directions. We've established that they will displace the same while they are touching each other. And there's the third quantity that will be the same for both. That is incredibly obvious that people usually don't think of it.
Wait.
This is what happens when you come in late. Go ahead.
Oh.
Forces has already been taken care of. We don't need to do any more forces.
Oh, okay.
Would it be time?
Yes.
Uh,
They touch each other for the exact same amount of time. Now, there's a lot of physics that we're doing right now. This is known as classical physics, that once you get into quantum physics, things get a little bit funky and you can usually find an exception, but I don't think there's an exception for that. They will touch each other for the exact same amount of time. So the time for A, or change in time if you want, is equal to the change in time for B. Now, the reason I go through this exercise is more than just to torture you. The reason I go through this is this introduces the next 2 major concepts. If I look at these concepts right here, I am talking about energy and work. If I look at the force and the time, I'm looking at momentum and impulse. And so we're going to still go through the analyses that we've been doing, except we're going to look at it from a different point of view. The advantage of dealing with this is we generally have to look at what happens before and what happens afterwards. We don't care about what's happening in between. So if momentum is conserved, which it should be in my nice ideal scenario here, if momentum is conserved, I don't care about the forces that the interaction of forces while they're touching. I care about what are they doing before the collision, and I can predict what's going to happen after the collision. So let us start out with work. I'm going to start out with this idea of course, black on black as usual. Work, symbolized by a capital W. This is one of the reasons I don't use capital W for weight. Work is defined as force, dot product, displacement. And we probably talked about dot products, but probably didn't go into too much detail on it. This is the point where we really need to have a pretty decent handle on it. So if I have a vector A and a vector B, if I add them, I can do head to tail, subtract them, I can add the opposite of one of them. Multiplication, there's 2 types, dot product and cross products. The vector multiplication. And let's go for the smaller one. All right, so there's the dot product. and the cross product. Dot products are called dot products because the symbol you use for multiplication is a dot. A cross product, the symbol you use, it's an X, but you can think of it as a cross. When you're multiplying dot products, or when you're doing a dot product with vectors, you care about parallel. So this multiplies parallel. What do you suspect the cross product multiplies? I heard three voices at once.
Tangent.
What'd you say?
The tangent.
Not tangent.
No, adjacent.
If it's not opposite of parallel,
Perpendicular.
perpendicular. So it multiplies. Perpendicular. So you think about that, the cross, the axis basically, it's two perpendicular line segments. Dot product also has another name, it's also called a scalar product. Whereas a cross product is called a vector product. And then I put the next two bits in just in case you run across them. Dot products are also called inner products. And cross products are also called outer products. You tend to not see that language until you get into even more sophisticated math, vector math. But that probably is the last time I'm going to call it inner and outer products. I will tend to flip back and forth between dot and scalar and cross and vector. And I do want to put this point out for the sake of the language, in case you run across it. Well, first off, why do you suspect it's called scalar product?
Because it multiplies scalars.
No, we're multiplying vectors. If I heard you correctly. And it has something to do with the answer.
Answer's a scalar,
Yeah, and over here,
answer's a vector.
yeah, and this is the part, so as far as we're concerned, that's good enough. If you get into more advanced physics or potentially math, it actually, the product is officially not a vector, it's called an axial vector or a pseudo vector. As far as we're concerned, an axial vector / pseudo vector looks, smells, and tastes almost identical to a regular vector. The only place where the difference comes in is if you start dealing with reflections. We're not worried about that. All right, so I have two vectors here, and I want to multiply parallel parts. So I've got an angle here, which I will label as theta. So I need to figure out how much of A is in the direction of B, and how much is perpendicular to B. So I would break A up into components. So I have one in the direction of B and one of them perpendicular. There's my right angle. This angle here is theta. And as we have done so many times, the adjacent side here is the hypotenuse times the cosine of that angle. And the perpendicular one is the hypotenuse times the sine of the angle. So when I multiply these, I multiply parallel parts. So A dot B is going to be A cosine theta times B. It's the part of A that's parallel to B, and then you just multiply the parts. Likewise, I could also got A, I've got B, angle theta here. I could break B up instead of breaking A up. So if I break B up, I've got a part that's parallel to A and a part that's perpendicular to A. The part that's parallel, well, that's the adjacent side, so that's B cosine theta. The opposite, B sine theta. And so A dot B in this case would be A times B cosine theta. Which is just what we had before, just by the associative property of multiplication. Notice also, commutative property holds. A dot B and B dot A are the same thing. It does not hold for cross products. Let's just do two quick and dirty problems here. So if I have a vector 3 newtons, comma 45 degrees, dot product with 4 meters, 30 degrees. The answer will be, well, first multiply the magnitudes. So that would be 12 Newton meters times the cosine of the angle between them. Well, what's the angle between them? So whatever 12 times the cosine of 15 is. I guess 10.73. What is it?
11.59.
So if I've given the vectors in polar form, I just multiply the magnitudes and then the cosine of the difference in the angles. If you did the cosine of negative 15 degrees, you'd get the same answer. And then the other example is that if you have it in rectangular form, that is also, we don't have to put it in polar form. If I have them in rectangular form, that's relatively simple. If I have 4 newtons I hat